Okay, let's kick off. Hello, everyone, and welcome to this seminar on modern reinforcement learning. So we are going to have this seminar in two parts. So the first one, we are going to cover the reinforcement learning for generative AI. And then in the second part, we are going to cover the RL for agentic AI. So this is the agenda for today. So we're going to have a quick context of RL and its evolution. Then we will cover the role of RL for generative AI, and then start to cover some of these key RL techniques that can be used for LLM alignment and also generative AI improvement. And then we will conclude with some of these advanced new RL techniques which improve the performance and the alignment of the LLMs. Okay, so let's start with this quick context on the evolution of RL. So RL has come a long way from its root in solving traditional control problems, things like balancing a pole or controlling the robot's arms. Today, at its core of how modern AI systems learn to make decisions in dynamic, uncertain environment. What makes RL so powerful is that it acts as a bridge between two worlds: the statistical training we see in supervised learning and the real-world goals that involves human preference and utilities. In other words, RL helps AI not just predict outcome, but also decide what to do to achieve the best possible result, whether that's optimizing energy use, improving recommendation, or aligning the model output with human values. But like any other kind of techniques, there are like some challenges. So traditional model, those trained using maximum likelihood estimation, are usually great at statistical fidelity. They can reproduce data patterns with impressive accuracy, but that accuracy alone does not always translate into usefulness. This is what we call the gap. So even if a model prediction are statistically sound, they might still miss the mark in terms of what humans actually want. The output could include the subtle artifacts, inconsistency, or fail to meet subjective preference or utility-based goal. RL is here actually to just offer a solution that can close this gap. So instead of optimizing purely for data accuracy, RL directly target human or utility-driven objectives. So RL usually learns through trial and error, evaluating actions, receiving feedback, and then adjusting until it aligns performance with real-world or preference-based success. So generative model, or most of the time LLMs, today they are incredibly capable. So they can create lifelike images, videos, or even 3D structure. But despite that fidelity, there is still a key limitation in how they are trained. So as we already covered, maximum likelihood estimation, or MLE, focuses on reproducing data distribution, not on meeting high-level human goals or value. That's where the strategic role of reinforcement learning really comes in. RL actually allows us to optimize for what truly matters beyond pixel perfect accuracy. It can handle objectives that are not differentiable, things like user satisfaction or ethical alignment that traditional training cannot directly optimize for. It also incorporates preference-based or preference-driven feedback, so model can adapt based on what people actually value. And beyond that, RL excel in dealing with temporal structure, decisions that unfold over time, and in imposing human utility constraint on what the model produces. All right, now let's talk about two paradigms of generative policy learning, which is actually two paradigms that can help to apply RL for generative AI. So when we talk about the generative policy learning, there are really two main patterns. The first one is block box approximation. In this approach, we treat the generative model like any other neural network and apply its standard reinforcement learning techniques. Things like policy gradient methods such as uh, DASR, CPQL, and Flow PG usually fall under this category. It's straightforward and flexible, but does not necessarily take advantage of the unique properties of generative model. The second paradigm is internal mechanism leverage, which goes a step further. So instead of treating the model as a black box, it taps into the model own mathematical structure, how it represents probabilities or latent space, to make policy updates more efficient and also informed. So we have like techniques like DivPO or QVPO, which use the generative model internal workings to improve performance and stability. So in short, the first approach relies on general purpose optimization, while the second the second method exploit what makes generative model special, leading to smarter and often more sample efficient learnings. All right, so far RL, so it actually just for the generative AI we are dealing with the generative model, like whether it's LLMs or like multi-model LLM. So whether you can consider that LLM as a black box, so goes under the pattern first, but then if you use the internal mechanism within the model when you are training the RL techniques, that goes on the second approach. All right, now let's talk about some of the techniques and paradigms for LLM alignment. So when it comes to the aligning LLMs with human preference, there are two paradigms that I think most of you know. We got this reinforcement learning from human feedback, or RLHF, and direct preference optimization, or DPO. Both aims to make model more helpful, safe, and aligned with what people actually want. But there are like two different routes. So RLHF follows a more traditional reinforcement learning pipeline. So it collects human feedback to train a reward model, which then guide the LLMs through iterative optimization, essentially teaching the LLM to generate response that earn higher reward from human evaluators. The DPO, or direct preference optimization, simplifies the process. So instead of training a separate reward model, it directly uses preference data to adjust the model's parameters, aligning behavior in a more stable and efficient way. So in a sense, RLHF uses explicit reward model, while DPO embeds the preference learning directly into the optimization itself. So two distinct routes but complementary paths toward aligning AI behavior with human intent. Let's talk about each of these models. So we start with this the reward-based one, which is RLHF. So as we know, like it's known for as reinforcement learning for human feedback. So and then there are three key stages for this. So the first stage is supervised fine-tuning. So here the model is trained on carefully curated demonstration data, example of high quality responses, and these steps actually establish a strong behavioral foundation, showing the model what good look like. Then we have the reward model training. So human animators compare pairs of model response and indicate which one they prefer. Those preferences are then used to train a separate reward model that effectively learns to score how satisfying or aligned responses is from a human perspective. And finally, we have policy optimization. We have algorithms like PPO, or proximity policy optimization, that are used and then to fine-tune and maximize the learning reward while staying closer to the original behavior through a KL divergency penalty. This balance ensures the model becomes more aligned with human preferences without drifting too far from what it already knows. So proximity policy optimization, so which was actually the algorithm to optimize the rewards solution, it actually becomes the industry standard for LLM alignment. Even even though that the newer algorithms have emerged, PPO continues to dominate practical application across major AI labs. So the main reason is the stability. So PPO offers a very controlled optimization process, and it prevents overly aggressive updates that could destabilize the training, which is critical when working with massive models. It also it's usually robust against high variances, meaning it can handle the noisy, unpredictable feedback that often comes from human preference data. Another key strength is its constrained policy update. So PPO uses a clipping mechanism or KL penalty to ensure each update stay within safe bounds, keeping the learning process smooth and predictable. And importantly, it can scale well, making it especially effective for billion parameters models. So in terms of the computation, so we all know that when training large language model with reinforcement learning, computational efficiency become a major consideration. And the environment these models operate in, the what we call it more like a kind of the LLM environment profile, is quite different from the traditional RS setting. So generating text sequences or rollout is relatively inexpensive compared to running full value function passes, which can be very costly at the scale. This is where we got this generative policy optimization, or sorry, the generalized policy optimization, or GRPO, which offers a more efficient alternative by replacing the full advantage function with a smart approximation. So in practice, this means we can avoid heavy value function computation while still getting strong policy improvement, which greatly actually reduce the training overhead. And because generating on policy data, meaning data sampled directly from the current model, it is already cheap and plentiful, and the typical advantage of policy method become much less significant. In short, LLMs make on-policy approaches both practical and efficient, reshaping the usual trade-offs seen in reinforcement learning. Now let's talk about the DivPO, which is more like a kind of the reward-free paradigm. So we already talked about the RLHF, which was the reward-based paradigm. Now let's talk about the DivPO, which is direct preference optimization. So DivPO was designed to simplify the alignment process by removing one of the RLHF most complex component, which is the separate reward model. So instead of training a reward function and then optimize that, DivPO directly incorporate human preference data into the model training objective. So it defines a loss function that compared preferred and rejected responses, encouraging the model to increase the likelihood of the preferred one relative to both the rejected outputs and also a fixed reference model. This approach streamlines the entire alignment process. So there is no need for additional reward modeling or policy optimization loops. So DivPO essentially turns human feedback into a direct, efficient training signal. So the result is faster, more stable, and then more stable fine-tuning that still preserve the alignment quality. So let's talk about the comparison between DivPO to PPO. So the trade-off really comes down to simplicity versus robustness. On the strength of DivPO shines in setting where we want to control clear, specific attribute like tone, sentiment, or style. So it's efficient and also can often match or even outperform PPO in simpler single-turn dialogue tasks, where the feedback signal is straightforward. It has streamlined the training process and also makes it easier to implement and tune. However, DivPO shows its limitation in more complex domains. So in tasks like code generation or multi-step reasoning, PPO still tend to deliver a stronger, more consistent result. DivPO can also be more prone to overfitting. So especially when preference data is limited, since it lacks the stabilizing reward modeling layer that PPO provides. And then in short, DPO offers elegant simplicity, but PPO remains the more battle-tested choices for larger scale, high complexity alignment. So let's talk about this stability priority in more details. So the industry continue preference um, for PPO over simpler version of the DPO, and that it's more like around the stability, which is the priority for the industry. While DPO offers a cleaner one, more streamlined, larger scale environment work usually deal with enormous model, noisy feedback, and large training results and training runs. And stability can quickly lead to degraded policy or wasted compute. So even though that DPO is conceptually elegant, practitioners consistently choose PPO because it minimizes the risk of catastrophic divergence. The reward model challenges. It is very important, especially for the RLHF. The reward model often struggle to generalize beyond the data that were trained on. So if the model encounter responses or topic outside the distribution, its judgment of good versus bad can become unreliable. Secondly, another challenge is they are highly sensitive to ambiguous human feedback. When annotators disagree or preferences are not clear, the reward model can pick up noise, which leads to inconsistent or unstable learning signal. And then because of all these weaknesses, stable policy optimization methods like PPO are absolutely essential. So PPO provide a robust framework that helps absorb these inconsistency and maintain reliable performance. Now, let's talk about some of these advanced RL architecture. We already covered those classic one, RLHF versus the DPO. Let's talk about some of these advanced one. So here, we are introducing an important conceptual shift in how we think about optimal policy in the context of generative AI. Classic one, optimal policy means zeroing in one which actually can best answer, essentially identifying the single highest utility response. But as generative models become more powerful and capable, this definition is evolving. Instead of just targeting one ideal outcome, we are now focusing on capturing the entire frontier of high utility solution. That means modeling a range of diverse high quality output, each potentially optimal depending on the context, user preference, and also downstream user. This is where DivPO makes a breakthrough. So it introduced mechanisms that preserve or even enhance output variety while keeping the same high standard of response quality. Let's talk about this DivPO or diverse preference optimization, which represents a significant step forward in alignment research by directly addressing the quality diversity trade-off that the classic preference optimization struggle with. So instead of forcing a model to collapse toward a narrow set of safe high quality output, DivPO integrates mechanisms that explicitly encourage diversity within the preference optimization process. So it allows the model to explore multiple valid ways to satisfy human preference, producing outputs that are not only high in quality but also varied in a style, structure, and perspectives. So in short, DivPO reframes alignment as a balance between excellence and expressiveness. So it keeps model faithful to human intent while preserving the creative breadth that makes generative AI so powerful. So let's talk about this strategy. So it's actually built on a clever and intuitive idea. Teach the model that diversify itself is part of what defines a good response. So it starts with the strategic selection. So instead of just picking any preferred responses, DivPO intentionally select the most diverse high quality output as the chosen example. This ensures that the model does not just repeat one type of good answer, but also learn the variety within the quality also is valuable. Then comes in the rejection criteria. The system identified the least diverse low quality responses as the rejected example. This contrast reinforces the signal that narrows repetitive outputs are undesirable. Through integrated learning, the model absorbs both signals at once, optimizing for human preference and diversity. The result is a model that can produce multiple high-quality output that differs in tones, structure, or approach, enriching the overall expressiveness of its generation. So, in terms of the diversity criteria, um, so we need a clear, actually a measurable way to define the diversity. One approach is the model probability. Here, responses that the model itself assigned lower probability to are considered more diverse. The reasoning is simple. If the model rarely produces a certain phrasing or structure, it's likely offering something novel. A second method looks at inverse word frequency. This captures diversity through language use. Responses that include rare or less common words are treated as more distinctive and also varied. And finally, there's an LLM judge approach. In this case, LLM is prompted to act as an evaluator, directly assessing which responses are most diverse based on content, tone, and also structure. Now let's talk about another method, Generative Flow Network, or GFlowNets, which is a fascinating architecture innovation in reinforcement learning. Unlike traditional or classic RL methods that focus on finding a single optimal solution, GFlowNet are designed to sample from a distribution of possible solutions where each outcome's probability is proportional to its reward. So this means that instead of chasing just one best answer, like similar to the previous DivPO approach, GFlowNet also models the entire reward landscape, learning to generate multiple outputs that all reflect varying degree of quality and also desirability. The core idea here is to balance exploration and also exploitation in a principled way, allowing the model to present diverse high reward options rather than collapse into a single one. And in practice, this makes GFlowNets especially powerful for areas like scientific discovery, where we don't want just one candidate molecule, design, or hypothesis. We want many promising ones. By generating diverse, high-quality possibilities, GFlowNets bring robustness and also creativity to problems where variety truly matters. How it works? So the key advantage lies in computational efficiency again here as well. Classic sampling methods like Markov chain, Monte Carlo, or MCMC requires repeated slow iteration to explore a distribution. GFlowNet, on the other hand, amortize all the efforts into a single trained generative model. Once trained, the model can produce a diverse sample in just one forward pass, dramatically speeding up the exploration. The training mechanism here is built around the concept of flow balance with a directed acyclic graph or DAC of possible generation trajectories. Each trajectory represents a sequence of decisions leading to a final output. Using a trajectory balance loss, the network learns to maintain consistent flow of probability mass across all paths, ensuring that the overall sampling behavior matches the desired reward proportional distribution. So in short, GFlowNets combine the diversity-seeking power of probabilistic sampling with the efficiency of a learned generative model, making them a compelling bridge between reinforcement learning and also probabilistic inference. So while GFlowNet excels at exploring diversity, high rewarding region, they do have a notable performance boundaries. Because their design encourages broad exploration, they can sometimes struggle to consistently generate the single highest reward samples, especially in larger or complex search spaces. This tendency toward over-exploration means that while they find many good options, they might not always zero in on the absolute best one. To address this, researchers have developed local search GFlowNet, which introduce a more focused balance between exploration and exploitation. This model guides sampling through localized search strategies, using both forward and backward policies to refine the search around promising region. In essence, Local search GFlowNets preserve the original model's diversity advantages while adding a layer of precision, helping the system not just explore broadly, but also converge effectively to top performing solution. All right, now let's talk about the multi-model alignment. So we all know that these days we are not just limited to the LLMs. We have also multi-model LLMs, and reinforcement learning alignment is also essential for those one as well. So as these multi-model LLMs handles input and output across multiple modalities like images, videos, and text, the complexity of aligning grows significantly. We are no longer just teaching a model to produce coherent language, but also to correctly interpret and also generate information that involves recognizing entities, understanding special relationships between objects, and also grasping the sequence of events over time. One area where this becomes especially challenging is video language alignment, or VLA. Aligning language with visual content in motion adds a layer of difficulty in preserving fine-grained perceptual understanding. So a key goal here for multimodal alignment is to ensure that as we push these models to become more general and capable, we don't lose the subtle but crucial details in perception that makes their output accurate and also meaningful. So visual foundation model, which is actually the core for many multi-model system. The main challenges for these types of model is to preserve the fine-grained perceptual understanding that these pre-trained VFMs already have. And when we align them with multi-model language model, especially during downstream training, there is a real risk that the rich visual information can get diluted. So a promising solution named regularization strategies can be used. These are techniques designed to explicitly align the internal visual representation of the multimodal LLM with the feature learned by the VFM. So in simpler terms, we are making sure that the multimodal LLM continues to see the world with the same clarity and precision as the original visual model, even after alignment. This kind of alignment helps maintain visual fidelity while still enabling the model to integrate and reason across different modalities. All right, so that was for part one of this seminar, which was on generative AI and how we can implement RL. In the next part of this seminar, we are going to cover the agentic one. So stay tuned for that part as well. Thank you.